Hello everyone, welcome to this 15 minutes short video which we are going to look at the concepts behind calculus. And to begin with is just the concept of calculus can be dated back credited to Newton and Leibniz, who worked independently and then were able to describe the concepts about which today they're used as the basics of the current or modern calculus. Now, the coverage for today will just be on the basics which underlie the principle of calculus, which I believe will help the beginner to understand what's meant or what's behind calculus. Now, without losing time, so we can say the topic actually is basics of calculus. Now, as a historical background, both Newton and Leibniz, the concept started when they were trying to address the issue of area and the curve. So, in addressing the to find the area and the curve, where you don't have like a regular figure, but you have regular figure, so they tried to think about how can they come up with the area and the curve. Suppose you have a curve like this. You have a curve like this is the question. You have a curve like this, and you have this, and you have this. Now this is f of x. Now, if you want to determine the area on this curve, it can be a little bit tricky because this is not a regular. This is not a regular shape. It's an irregular shape. So to be able to determine the area on this curve, it needs a little bit more input. Now, but these guys, they just discovered that the area, if you have an irregular a curve which is described that way, the area and the curve is actually the summation of very small rectangular shapes which can be approximated. They're not exactly rectangular, but can be approximated to rectangular shapes with a very small or very little thickness. You can call it dx. This is x, and this is y of f of x. So they found out that actually the area under the curve is equals to summation of these small areas of rectangular shapes. I mean, they can be approximately rectangular shapes, and they will be of varying heights. Depending on the location, on the value of x, where x is. So this is one. If I have another one here, that infinitesimal, infinitesimal element, which this is number 1, this is number 2, then you can sum up all of them throughout. There will be varying heights depending on the location. So summation of these small elements or they can be aggregated to area under a curve. The smaller the width, the smaller the width, the more closer is the approximate area to true area. So here, the smaller the thickness of this element, then the more accurate is the approximated area, because we are actually approximating the rectangular area and this shape is not rectangular. So well, on calculating, they discovered that so the summation of all the areas of DAs is approximately to capital A. Now this summation is what nowadays we call integration. When you have very small areas, now with the limit we can say summation of this dA limit as dx approaches 0, which means the thickness here, the thickness of this element, as it approaches 0, then this one approaches to integral of dA, which is actually equal to area. So that's the introduction. That's the how they came up with the integral. Now also on the part of differential, you can hear something called differentiation. Differentiation is actually the same thing. Comes from the concept of derivative. Now this derivative is actually brought from the area. It's not the area. Is actually obtained from the gradient under curve. Now, gradient under curve, what is that? Find the gradient under curve. It means you determine the slope of the curve. Now, for the beginners of calculus, we always know that we can determine the slope of a straight line by taking change in y over change in x. But what about when you have a curve like that, and you cannot just take 2 points, because and determine the change because it won't be the slope of the curve. In other words, the slope of a curve is varying. So, in other words, it depends on a position of x. Now, to get a closer look of that, consider you are having this curve here. Just like, let's take a simple curve going that way, increasing. So I'm not good at drawing. But at each point along this curve, at each point, you can see if I'm at this point, then it's likely, if I look at the closer points around this, it's like that my direction of travel, suppose you're traveling along this curve. Now, when you are here, it's like your direction of travel is along that line, for example. That line, and when you are at this point, your direction of travel is along that line. And when you are at this point, your direction of travel is along that line. So it means your inclination or slope changes with change in value of x. Now those values of x, here is x1, here is x2, here is x3. Now, so the calculus helps us determining that change as a function of x. Now, this has been evolutionary to the calculus, to the world today, which you can calculate the rate of change, which even that rate of change also changes. So you can get the rate of changes and small changes and other things. So nowadays calculus is applied in widely near every field. Calculus is applied in the field of engineering, in the field of economics, even to the biology, let's say, so human science, I don't know what they call, but it's applied in a wide range, in many fields, because talking about this concept of the rate of change and the curve, variable, because the whole concept of calculus is actually dealing with small changes to get big, to estimate. Now in the next this 30 by 15 minutes are going to be over. In the next video we'll be dealing with the first principles of differentiation, and also we can look at the determination of the area under curve. Thanks for listening of area under curve.